In this video, I'm going to build a plane with some crazy overkill, high lift devices that allow it to fly so slow that it almost looks like it's defying physics. But first, let's start with the basics. Everyone knows that airplanes use flaps to increase lift on takeoffs and landings. Flaps work by giving a wing more curvature, or camber. This decreases the pressure on the upper surface, which sucks the wing upward. The increase in camber also gives the trailing edge a steeper downwards facing angle, so the air flowing off it goes down. And if you push more air down, you get more lift up. You can only take the concept so far though. If you put the flaps down at too steep of an angle, the airflow will detach from the top surface and become turbulent. This is a stall. Stalls are bad because the wing essentially stops flying. One way around this is slotted flaps. If you separate the flap from the wing, additional air will come in and delay flow separation. Slotted flaps are used on pretty much all large planes and modern airliners. A few years ago, I built a plane that exploited this concept way more than any other plane. Instead of slotted flaps, it used what is essentially a slotted wing to keep the airflow attached even though the lowest wing has a super high angle of attack. This allowed it to fly really slow. It's the same concept as slotted flaps, just with entirely separate wings rather than just separated flap segments. It turns out that slotted flaps are not the only way to improve the performance of a flap. There's also a lesser known concept called blown flaps, or jet flaps. This is where you take high pressure air from the engine and pipe it through the wing and then out through a little slit right above the flap. This high pressure air stays attached to the flap at much higher angles of attack than the regular airflow would. So as a result, blown flaps can operate at steeper angles and generate more lift than regular flaps without stalling. I'm sure some people are wondering why the high pressure air doesn't just flow out of the slit in a straight line and separate from the flap. The reason is because of the Coanda effect. The Coanda effect causes air to stay attached to a curved surface. It's why you can blow out a candle from behind a bottle, and it's also why air stays attached to an airfoil in the first place. Without the Coanda effect, air would just separate around an airfoil and the wing would always be stalled. So by blowing air out of this slit right ahead of the curve, we know it won't just leave, but instead it will stay attached to the upper surface and prevent a stall. This footage shows the blown effect on a discrete airfoil rather than a flap, but the same concept applies. When high pressure air is blown out of here, the flow separation completely goes away and the wing is no longer stalled. There really aren't many airplanes that use blown flaps, mainly because they add extra weight and complexity. Slotted flaps are a much simpler alternative. Blown flaps are most beneficial on jets with small wings that need to increase lift as much as possible for landings. One classic example is the F-104 Starfighter. This plane was called a missile with a man in it, and it's not hard to see why. The wings are extremely small to reduce drag and increase its max speed, but this made takeoffs and landings pretty sketchy. Without blown flaps, the plane would land at around 220 miles per hour. With blown flaps, the landing speed was reduced down to around 155 miles per hour, so they really help slow the plane down a lot. For my own project, I want to take this concept and apply it to the opposite kind of an airplane, one that already flies slow, and see if it'll make it be able to fly even slower for super short takeoff and landing performance. So step 1 is to hop into Onshape. I used the Holbrook Aerospace Onshape template to import the S1210 airfoil. I chose this profile because it has a high coefficient of lift at the low Reynolds numbers that we'll be working at, and its top surface has a nice gradual curve that the Coanda effect is going to love. I modified it a little bit by thickening the rear section and the trailing edge, and then I started designing the rest of the wing. I'm not just adding blown flaps here, I'm going to make the entire wing be blown. And to take it even further, the plane is going to get 100% of its thrust from the blown wing system, so this should be pretty interesting. The plane will have 2 electric ducted fans, one on each wing, and those EDFs will blow air into big long cavities inside the wing. Here's a cross-sectional view. The fan will fill this cavity with high-pressure air and then it will shoot out through this slit and hopefully stay attached to the wing due to the Coanda effect. This is a pretty cool wing design if you ask me. I was super excited to test it out, but first we need to make the rest of the airplane. Since the goal here is to operate at high angles of attack, I designed a mechanism that would allow me to control the angle of incidence of the wing while in flight. The fuselage is very simple. It's just going to be made out of 6mm Depron. I gave it a T-tail to hopefully keep the horizontal stabilizer out of any downwash from the wing, since we might have a lot of that while flying at super slow speeds. If you want to check out this CAD model, it's available at the Onshape link in the description. I'm going to machine this wing out of pink XPS insulation foam on my 3-axis CNC router. This is going to be a 2-sided milling operation, so we first have to cut the workpiece down to exactly the right thickness, and then drill 4 holes to keep it aligned with pins in the bed while we flip it over later. The first real tool path is the bulk clearing operation. This just gets rid of the majority of the foam. And then after that comes the parallel tool paths. This cuts the final shape of the wing with a much higher level of precision. and then I did another one at a 90-degree offset, which wasn't super necessary, but it did result in a slightly nicer surface finish. Now I'm going to use these pins to index with these holes that I drilled in the top of the foam. 180-degree flip in this direction. That's that. Now I need to lock it down. Then it was time to machine the bottom of the wing, and hope that it aligns with the top of the wing. After all the machining was finished, I had to cut the wings out of the stock with a razor blade. In CAD, I had to model all these little tabs into the wing so that it stays into the stock piece and doesn't just fall out. Once free, it required some light cleanup, but all in all, it was looking pretty good. And of course, there are 2 wings on this plane, so I had to do it all over again for the other side. To make the wing less fragile, I'm covering pretty much the entire thing in 2mm packing tape. This is pretty time consuming, but it results in a super smooth surface finish. I even put tape down into the air ducts to make the exhaust slits more aerodynamic. I needed to be able to route the motor wires out of the wing, so for that I cut some teeth into the end of a carbon tube and used it to bore a hole through the foam. And here is the 50mm EDF going in. I'm using these 40 amp ESCs, and to save some weight I removed the aluminum heatsink blocks and bullet connectors. These ESCs will be getting plenty of airflow since they'll be inside the air channel. The motors then got glued into place, and I cut out these temporary little walls that just kept the wing from breaking in half during machining. To waterproof the ESCs, I smeared silicone grease all over them. Oh, did I mention this is a seaplane? Now it's time to make the curved plate that goes over the air duct in the wing. Step 1 was to 3D print a mold. I printed it in 2 halves, and those got joined with alignment rods and some Gorilla Glue. Next, I smeared on a bunch of epoxy-based fairing compound to cover all the 3D print lines, and I scored a trim line in that so that I know where to cut later. After that cured, I sanded it, and then sanded some more. Then put on mold release wax, cleared out that line again, and painted on some PVA mold release film. Next, I mixed up some epoxy and started wetting out the mold. This is carbon fiber tow that I'm laying down along the edges for a little extra rigidity. Then came some 12K 200 gram per square meter carbon fiber plane weave. This stuff is pretty hard to work with compared to normal 3K plane weave. Not my favorite, but it does look more expensive, which is cool I guess. I did 2 layers of that in total, and wetted it all out with the epoxy resin. After that I took a piece of Mylar that had previously been waxed, and laid it over the top. Then I used a credit card to squeegee out all the air bubbles. After that came some breather cloth, and then it went into the vacuum bag. These are the cheap vacuum bags made to store clothes and stuff in your closet. They're kinda hit or miss, but if you can get them to seal, they work pretty well. A few hours later, I opened it up. What do we have here? The big 12K weave doesn't make for as smooth of a surface finish as the finer weaves. Probably should have used 3K. Oh well, it'll work. Okay, now I gotta try and get it off of here. Weird question, but have you ever shined a mirror through a window to illuminate a room inside your house? It's actually a really nice color quality of light, and it's super intense. I've always wanted to build a sun tracker that automatically pointed a mirror into my window throughout the course of the day. Now what if I told you there's a company getting ready to launch thousands of mirror satellites into space? And instead of lighting up a room in your house, they're planning on lighting up entire solar farms at night. It turns out this company really exists, and they're also undoubtedly the coolest sponsor this channel has ever had. Now I know this idea sounds crazy at first, but it's actually already been done. In the early 90s, the Russians launched a foldable mirror into space with a 20-meter diameter, and it was briefly able to reflect a beam of light onto Earth that was about 4 kilometers wide and had about the brightness of a full moon. Reflect Orbital's plan is to do this, but with a lot more mirrors. They'll be constantly orbiting the Earth around the sunrise and sunset, and with enough mirrors aimed at a solar farm, it will be able to start generating power a few hours before sunrise and continue generating power for a few hours after sunset. And that's just one application. They'll also be useful for all sorts of other things, only limited by your imagination. This company is co-founded by Ben Nowak, and Ben and I have been subscribed to each other on YouTube for well over 15 years. His more recent channel, Ben N Builds, is so entertaining. He's been doing wild stuff for so long, such as 125cc snow thing, random helium liquefier, deep sea ROV, climbing Denali, DIY jet engine, DIY iron furnace, DIY nuclear fusion, 40-watt laser, DIY thin film high vacuum deposition, and now putting mirrors in space. They also have Charlie Garcia, who is like the rocket engine guy, and a homie. These guys are probably the smartest people I know, and if anyone can pull it off, it's them. And now they want you. Reflect Orbital is aggressively hiring mechanical engineers, makers, builders, and creative problem solvers passionate about aerospace and innovative engineering challenges. They're currently gearing up for their first satellite launch, which could be as soon as April 2026. Reflect Orbital recently secured a $20 million Series A funding round led by Lux Capital with continued support from Sequoia Capital. If you love aerospace, cutting-edge technology, building novel solutions, and building things that will have a large impact on the future, then Reflect Orbital is the perfect place to put your skills to work. Check out the link in the description for more info. Now back to the video. Okay, well that looks pretty good. Next I trimmed them down to size with a Dremel and sanded the edges straight. Look at that, it's flying flying already. So despite being carbon fiber, this thing is definitely not very stiff. I think this thing will still work because it's being constrained pretty frequently along the air gap on the wing, but the flimsiness is definitely not great. Oh yeah. For the second one, I made the mold the opposite shape so that the top was smooth and the inside was bumpy. I also 3D printed them in the vertical orientation so that the layer lines were finer, and that ultimately resulted in less fairing compound and sanding. Oh yeah. Huh, that looks pretty good. Then I cut a big chunk out of it for the EDF to fit in. Now it's finally time to attach the carbon cover to the foam wing. To do that, I'm just using Gorilla Glue. I smeared that all over the mating surfaces and was careful not to use too much since it foams up. And then I carefully laid the carbon in place. Oops, forgot to plug the wire pass-through hole so air doesn't just leak into the fuselage. Then I closed it up for good. This is a little EDF cover thing that will help direct the airflow into the wing cavity. It's 3D printed from PETG, and I simply glued that into place. Then I did some packing tape over the seam and weighed down the cover while the glue cured. Next, I 3D printed a tattoo gun. Join me and my new non-profit, Ink Side Out, as we work to distribute open source tattoo guns to prisons across America. Just kidding, it's actually a needle cutter used for cutting foam board. I don't have a laser cutter, so I decided this was the next best thing. But after using it, I really don't know if it's any better than just using a 1mm end mill would be. It did work well though, no doubt about that, and now I don't have to fuss around with printing paper plans and cutting them out and all that. I'm not going to cover the rest of the build with too much detail since it's a fairly normal foam plane, but I did try and use Gorilla Glue for everything since it's much lighter than hot glue. That's tricky though because you have to tack everything in place with pins or tape while the glue dries. Here's the mechanism that allows me to change the angle of attack of the wing. Pretty straightforward, just a servo and a push rod, and a cam type of thing. And that whole assembly gets glued right into the foam fuselage with Gorilla Glue. At first I thought I'd be able to get away with controlling roll through differential thrust, since the motor RPM will be influencing lift, but then I got scared and just decided to cut some ailerons into the wing. I also covered the entire bottom of the fuselage in tape to increase smoothness and durability. Now to finally attach the wings. I first slid these 6mm by 1m carbon tubes through the fuselage, and then those just got glued right into the slots that were already cut out by the CNC machine. Pretty easy, and then I just taped over everything to make it more streamlined. And that pretty much concludes the airframe build. But there were still a few finishing touches that I had to do, like cutting out the hatches and installing a flight controller. I'm using ArduPilot, mainly just for the flight stabilization, but it does have a GPS, so it should be able to fly autonomously. Now I know anyone familiar with RC planes is thinking, what in the heck kind of EDFs are those? These are basically the same thing as those little 100,000 plus RPM fans used in Dyson hair dryers and the handheld air dusters, but they're just bigger. These have a 50mm diameter and are rated for a maximum of 450 watts. The cool thing is that they are extremely well balanced, so they have virtually no vibration. They're also quite a bit quieter than hobby EDFs. I'm honestly not sure what products these are used in, probably just bigger hair dryers, but IDK. These fans also have a lower blade pitch than hobby EDFs. This means they'll make more static pressure, but the downside there is that they wouldn't push an RC jet as fast if you used one in it, unless you constricted the flow, but I'm not really sure if that would actually make it any faster than just a normal EDF with higher pitched blades. Speaking of constricting the flow, I did a lot of testing with different sizes of exhaust diameters, not only with these 50mm metal fans, but also with a normal hobby EDF. And it turns out that the metal fans don't lose thrust as much when you constrict the flow. If anything, they might actually make more thrust with a 35mm exhaust diameter, whereas a normal hobby EDF starts to choke right when you start restricting the flow. So, this data made me think that the metal fan might be the better option since we need to restrict the flow and force it out of all these little slits in the wing. I tried to size these slits so that they cumulatively have the same cross-sectional area as the 35mm nozzle, since that was what gave the best performance on the test stand. With a 4S 1300 mAh battery, the all-up weight is 2.7 pounds, or 1,224 grams. Okay, finally it's time to fly this thing. Here's me attempting to make a thumbnail like a good YouTuber. For this first test, I'm going to try a 4-cell 1300. I don't know if this will have enough power. Let's put this thing in the water, see how the ground handling is. It floats. One wingtip is underwater. That's not great. I might need to build some wingtip pontoons. Well, I can steer it. That's good. It goes. Oh wow, holy shit, it flies. I didn't even mean to take off. I was just gonna do a taxi test. It flies really well. I'm not even in fly-by-wire A mode, it's just fully manual. Wow, I need to move the battery just a tiny bit back. Oh, it glides pretty well. Downwind. So graceful. Wow. Huh, is my battery dying? Oh, flared way too early. So now I'm gonna try the 6-cell battery. This is a lot heavier, so I think I'm gonna need to put it further back. Now we should have tons of power. So notice that with this flight, I'm taking off with the wings tilted back to the middle position for a bit more of an angle of attack. Having the wing in the middle position clearly helps me take off a lot more quickly, but I still haven't tried the wing in the steepest position yet. So here I tried lowering the wing from the middle position to the lowest position, and what I didn't realize at the time was that it didn't actually move. It seems to fly well. Oh, the hell was that? No, I have no idea what happened. It just completely lost power. Oh man, that sucks. I was looking at the battery voltage on the transmitter and it was still reading like 21 volts. I'm downwind of it now, but it's not coming this way very quickly, so I might have to swim. At least the wing is in one piece, it seems. Patience negates the need to swim. About 10 minutes later, it's here. And this is not looking good. Oh man. So what happened is that my wing tilt servo didn't have enough torque and couldn't actually tilt the wing. So when I had the wing tilt switch in the lowest position, the servo was just pulling its stall current for the whole time, and that caused the little 5-volt regulator in the flight controller to brown out. I should have used an external BEC, but luckily I was able to get the plane glued mostly back together, and I also installed a 3-amp BEC, so we were ready for another test. And we back. It's not very calm today, a bit breezy. Oh, it's blowing downwind quick. I gotta take off. Oh my god, it's so loud. One of the motor bearings got corroded after the last crash, so that's why it's noisy now. Just levitates. 21.8 volts already? Jesus Christ, is the battery actually dead? Battery is fairly warm, so I believe that it could be dead already. So yeah, it turns out this is not an efficient plane. It just sucks down batteries, like even twice as fast as a 5-inch FPV drone. But we didn't build this plane for efficiency, we built it to never stall. Okay, I'm gonna put the wing all the way down. It's not going. I think the servo is just stalled. Let's see how fast it'll take off with the wing all the way down. I'm not gonna completely fly, but I just wanna do a little takeoff. Wow, it takes off so fast. Man, I really want to fly it with the wing all the way down like that now. Oh wow, there was a lot of water inside this wing channel. I hope I waterproofed those ESCs in there. Oh, and there's a lot of water in there too. Oh man. So here I figured that before I crash again, I should use the line laser and a fog machine to try and get a better look at what's going on with the flow around this wing. This is just with a fan blowing at the plane, so the flow is not laminar like it would be in a wind tunnel, but we can still kind of see what's happening. With the motor off, the flow just kind of diverges from the upper surface and leaves going straight backwards. With the fan on, the flow gets pulled down a bit more to match the contour of the surface of the wing. Who am I kidding? You can hardly see anything from these clips. Honestly, I'm just showing them because the laser looks cool, but here we can see that the duct system is indeed working, and the flow seems to get pretty evenly distributed over the entire length of the wing. These clips here show that this wing has the ability to move a lot of air down, and the air doesn't even have to flow through the fan or around the wing to be affected. Even the surrounding air gets sucked down over the higher velocity airflow that's coming out of the slits. All the air getting moved down creates lift, but that lift isn't cheap. We're really just burning watts to make lift here, like a drone hovering. It's definitely not efficient lift like a wing makes in forward flight. But that's not to say the blown wing system doesn't at least help the wing generate its own lift in a decently efficient way. Now back to the lake. On this day I was flying a 2200 mAh 6-cell battery, which is much heavier, and it didn't seem to have much of an effect on the slow flight performance. Wow, that is definitely a super short takeoff. For these flights, the wing tilt servo is trying to hold the wing all the way down, but it just couldn't hang. So I decided to throw some tape in there to fix the wing in place. It's entirely possible that this thing just stalls really bad. Oh yeah. Oh yeah, it takes off real quick. I'm having to hold full down elevator. And I don't have a bailout because I can't put the wings up. Look at this thing. Wow, that's amazing. It's in fly-by-wire A mode right now. I'm not sure that I would even be able to control this thing without the autopilot. Yeah, man, this big battery is so hot. I want to try putting it in return to home mode just to see if the autopilot works at all. Wow, this thing is just trying to float out of my hand. Look at this. I'm pushing this thing with one finger. Whoa, this is so cool. Woo. Arming the motors, walking along, and throttling up. Man, that's too good. Okay, now it should be in return to home mode. Yeah, it's doing it. It's circling. It's working. Wow, I didn't think return to home mode would work with this flight controller because it seems really janky. So I know what a lot of you are thinking. You're thinking, of course it's going to take off fast and fly slow. You've been going directly into the wind. And this is true. Now we get to see what it looks like with zero wind. Still pretty short. Yeah, that is so cool. Holy shit, it still floats. Even with no wind. It floats better now. Wow. Look at that thing. For how heavy this plane is, that is insane. I mean, it's not a heavy plane, I should say, for how much it weighs. Look at this. Wow, that is incredible. I mean, there's other planes that can fly this slow, but they're made of like Mylar and toothpicks, or just like 2D super thin Depron planes. This one is full 3D, and it has a big fat fuselage, and it's got a big fat battery and two really heavy motors. Oh, it's getting a little stally right there. Oh, is it in? Oh, whoa, I took off without it in fly-by-wire A mode right there. It really needs the stabilization at this low speed. Yeah, look at this. I can keep up with it no problem. Oh, that's a stall. Oh man, okay. That's actually really interesting. When I cut the throttle there to try and glide in and land, it didn't glide. So I think it really does need the air blowing over the wing to stay up. I'm gonna try a heavier battery now just to see what it's like. This thing is toasty. I'm gonna try a big fat 2200 6 cell now. It's definitely not gonna fly as slow now. Wow, but it still flies really slow. Oh man, this thing is so cool. This thing is even way slower than my multi-element airfoil plane. No doubt. For the weight, it's way slower. It's a little harder to keep up with. Well, when I hit the gas, it just levitates upwards. It's like the plane does not even need to pitch up to climb. So right when I let off the gas, dropping the throttle, pulling back, and it definitely drops the wing. It needs that airflow. Even if I don't pull back on the stick, I'm gonna try just dropping the throttle and letting go and seeing, oh yeah, it still drops the wing. Luckily, it's really quick to recover from. So this goes to show that at this angle of attack, it really needs the airflow over the wing to stay up. But if I hold full down on the elevator, it can glide. It just doesn't like to. This thing is too cool. I'm so stoked. I don't know how these ESCs have not burned out. Because if I'm pulling enough amps to make this big old battery really hot within 2 or 3 minutes, then I would think that I'm cooking these ESCs because they're not very big. I already forgot which ESCs I put in it, but they're not that beefy. Okay, back to one of the smaller batteries. This is the 1000 milliamp hour 6 cell. See if I can do a turn in this tight area. Yeah. Woohoo! Look at that thing. It's too cool. I can feel the airflow. Whoa, it just did like a Tokyo drift. Today I'm gonna load it full of batteries and wire them all in parallel. Oh, she's heavy. She's heavy, but she's up. Wow, and it still flies pretty slow. This is when I'm gonna burn out the ESCs. Man, I did not think it would be this slow at this wing loading. It's like not that much faster. Look at this thing. It just freaking floats. Oh, I gotta do a tight turn here. Okay. Now's probably a good time to talk a little bit more about wing loading. With the 3 batteries in it right now, the wing loading is 14 ounces per square foot. The E-flite Super 1.7 meter timber has a wing loading of 11.7 ounces per square foot, and the 1.2 meter timber has a wing loading of 15 ounces per square foot. and both of these are clearly nowhere near as slow as this blown wing plane.
This thing is too good. Okay, now I'm gonna climb up to do some stall tests. Wow, those ESCs are probably so hot. Oh, and there goes one of them. Okay, come on. Oh no, oh no, oh no. And that's the end of that. Oh man, it just went into a stall spiral and would not leave. Oh man, the fuselage is smashed again. Oh, crap. Oh yeah. Oh yeah. That's definitely burnt out this motor. Holy crap, this metal on the outside is even hot. That's not even thermally connected to the, I guess the stator vanes are metal, so that could transfer heat out. That motor in there must be insanely hot. Okay, well, that's the end of that. This thing is very heavy for how slow it was flying. Like, it's almost hard to hold with just one hand. If only that motor wasn't burnt out, I could still fly. Even if this plane was just powered by 2 normal 50mm EDFs just mounted under the wing like normal, I still don't think it would be that efficient, because just these small diameter fans in general are terribly inefficient.
Here's some data to back that up. Even a regular 50mm EDF produces 3 times less thrust per watt than a 10-inch propeller. Now, this is static thrust. The difference might not be as big at high speeds, but still, it goes to show EDFs are pretty inefficient. So is it a good idea to power your plane 100% from a blown wing system? It might lead to the best slow flight performance, but your flight times are always going to be crap. It seems like it would make much more sense to use the blown wing, along with a normal propeller that makes the majority of the forward thrust. But I still wasn't quite sure how much air we need to blow over the wing to make it unstallable, or at least impossible to stall within a reasonable flight envelope. All aboard the science machine. Damn, that's an iced out whip.
Ooh, it's tight.
We were on our way to go do some science, but Colin just got an Uber Eats delivery. So we gotta go deliver some pet food to some rich people. Well, that's a lot of dog food.
Steven needs his dog food.
High five.
Let's go.
Yeah, get that money.
$9 for
$9. Damn. Okay, now it's time for science.
Oh man. Oh, it's making so much lift.
So for those of you who don't know, when the ribbons on the back of the wing start to go crazy, that means it's stalled. When the ribbons all look like they're blowing backwards, that means the wing is not stalled. So with the fan off, the wing seems to stall at about a 19-degree angle of attack, which is in line with what Airfoil Tools says.
1200 microseconds on the PWM.
With the throttle on even just a little bit, the wing now didn't stall until like 29 degrees, so that's a 10-degree improvement.
Oh yeah, that seems to work pretty well. 1300 microseconds on the PWM. Oh yeah, it stalls real late. Wowee, okay.
Here it didn't go into a deep stall until like 36 degrees, and the onset of the stall was a lot softer.
I know this guy.
On the bike?
Yeah.
Who is
Hey
it?
Scott! I think we were going about like 13 miles an hour.
This is 15 microseconds. Oh yeah, it's like, it's still not even real. Okay, the front of the wing is stalled up there, but not the back of the wing. Okay, I'm gonna raise it a little bit more. Oh man. Oh, okay, yeah, the back of the wing like never stalls. It's only the front. And then here's no motor. Yeah, it stalls really easily.
So I only went up to 1600 microseconds, which is a little over half throttle, but even after like 1400 microseconds, it seems like there's starting to be diminishing returns. At any higher throttle levels, the front of the wing is still going to always stall at around 35 degrees, but at higher throttle levels, the back of the wing seems like it'll stay attached at much steeper angles. This made me think I should have put the exhaust slit further forward on the wing, then maybe none of it would stall. So, a super powerful blown wing does indeed seem like a cheat code to get a wing to perform extremely well at high angles of attack, and it did allow this plane to fly incredibly slowly for its given wing loading. But I can't help but wonder if there was something else going on here. The plane was flying around with an angle of attack of around 13 degrees, and the upper surface near the trailing edge of the wing is another 13 degrees steeper than the chord line, so all the air getting blown out of the motor is heading downwards at a 26 degree angle by the time it leaves the trailing edge. 26 is 29% of 90, so that means about 29% of the motor's thrust isn't even being used to push the plane forward. It's just being used to push the plane straight up. The cynic in me wonders if we were just to give this plane a normal wing, with the same EDFs, mounted on the center of gravity tilted up at a 26-degree angle, would the slow flight performance be similar? In other words, what I'm wondering is if it's actually the blown wing system that's keeping the flow attached to the wing that's doing the magic here, or is it just the fact that the blown wing system happens to direct 29% of the prop wash downwards rather than backwards, making this thing like 29% helicopter and 71% airplane. My best guess is that the blown wing system really is working wonders, and it's using that god-awful amount of power it's consuming to help the wing generate lift more effectively. When I had the plane loaded down to 4.2 pounds or 1900 grams, it was maintaining altitude at about half throttle. If we go to half throttle on the test stand, that's about 220 grams of thrust per wing, which would mean the plane's total thrust was around 440 grams. So if we assume 29% of the thrust really is going towards raw vertical lift, that would only be 7% of the plane's total mass. Right before the motor burnt out, I was climbing at about 80% throttle, which gives us 850 grams of thrust. Again, assuming 29% of our thrust is going straight into lift, that would only support 13% of the weight of the plane. So to me, that alone suggests the wing really is doing all the heavy lifting here, since there really just isn't that much thrust in general, and the blown wing system is just enabling the wing to make much more lift than it otherwise would. That said, I also feel like the blown wing system is probably not the most efficient way to make a plane fly super slowly. This here is called a quad plane. It's a type of vertical takeoff and landing airframe commonly used for drones. And I know this is totally cheating since it's no longer really an airplane, but with some big efficient propellers, I'm sure that a quad plane that weighs the same as my plane could do all the same stuff and more while consuming much less power. All that's just to say I don't think my 100% blown wing plane is very practical for any real-world applications, other than just being cool, which it definitely is. Later on I did some more thrust testing on the bench. I wanted to find out if using this metal fan was actually a good choice, as opposed to just a normal hobby EDF. So I removed the metal fan that was burnt out and replaced it with a normal 50mm hobby EDF. I ran each fan type up to 154 watts and measured the thrust. And I did the same for a bare 50mm fan that is not mounted in a wing, just for a baseline comparison. And it turns out the metal fan was definitely a better choice than the hobby EDF. This makes sense because the air ducts in the wing have a ton of drag, and we need that high static pressure to force air through it all at high velocity. But compared to just the bare fan alone, blowing air through the wing erases 27% of our thrust, which honestly isn't as bad as I thought it might be. So all in all, I think the blown wing system on this plane was super cool. It really did allow the plane to fly magically slow, and I'd like to do something like this again in the future. Maybe I'll combine a multi-element wing with a blown wing. That'd be neat. By the way, we decided to do a second batch of flick wings, so if you've been waiting to buy one, you're in luck because you still can. These things fly super well, and everyone I've talked to that bought one is really happy with it. If you want one, check out the link in the description. And the color shadow lamp has been getting great reviews too. People seem to love it, so I'm quite happy about that. The first batch has not yet sold out, so you can still get one, but they might not be in stock for too much longer. If you missed the announcement about this lamp from a few videos ago, it's basically just red, green, and blue LEDs on these pivoting arms. When all three are shining on a surface, you get white light. But anything that casts a shadow causes the light to get broken up into its colorful components. It's a fun effect to play around with, and a great accessory for photography. If you want one, check out the link in the description. That's all for this video. Thanks for watching. Bye.